Hello friends, I welcome you all to this session on graph theory. Today we will be learning about the theorem that is Havel-Hakimi theorem. So this theorem says that we have to write all the degrees or the degrees of all the vertices in a sequence such that it is in descending order, that is non-increasing order. Then what? Then we have to remove the first element of that sequence. Okay, and remember the weight of that element. So let's say if I'm having 2, 3, 1, 1 as the sequence, then I have to arrange it in descending order, and then I have to remove this element and consider that and see what the weight is. It is 3, so we have to mark 3 elements, 1, 2, 3, and then from these marks element we have to subtract 1, so it is 1, 0 and 0. So in this way this particular statement follows. Now the question it further poses that it tells that if you can't subtract, it's not a simple graph. So basically Havel-Hakimi theorem is used to check whether any given graph is a possible simple graph or is it graphical or not. So what we have to do is we have to first write the degree sequence in descending order, then we have to remove the first element, then take its weight and mark the remaining element and then subtract 1 from it. And if it so happens that I am unable to do it, why? Because the number are exhausted. What does this mean? This means, let's say instead of 3 this is 4. Now I have to mark 4 elements. So in this sequence, I have to go to first element, second element, third element. But the question is, where is the fourth element? It doesn't have. So that means this particular sequence is not graphical, not possible simple graph. So that is what this particular statement tells. And then once this is okay, then you have to go to the first step and repeat everything. Now there are few checklists which you should follow, that the degree sum of all the vertices in the sequence should be even, and no degree in that particular sequence should be negative. So this should not be there, and the degree sum should always be even. So to understand this particular theorem, so let us solve one problem. So the problem says that check if the sequence is representing a simple graph or not. Now the first thing is that we have to write this particular sequence in descending order. So I have written it as 3 3 3 2 2 2. Okay, this is now written in descending order. So let's say this is iteration number 1. Now what I have to do is I have to remove this element, and according to the weight of this I have to mark the elements coming next. So I have marked 3 2 2. 3 elements I have marked because the weight of this number is 3. Then what I have to do, I have to remove 1 from these numbers. That means 3 minus 1, 1 minus 2 minus 1, 2 minus 1 and 2. This 2 is coming as such because that has not been marked. So this becomes 2, 1, 1 and then 2. Then in the next iteration again we have to sort this sequence in descending order. So it will be 2, 2, 1, 1. Once this has been sorted, I have to remove this element and mark the elements after it based on the weight of this element. So the weight is 2, so I have to mark 2 elements. So what? Then I have to remove 1 from these marked elements. So this becomes 2 minus 1. Then this is 1 minus 1, that is 0 and then 1. And then this 2 minus 1 will be 1 and then 0 and then 1. Now in the third iteration I have to again sort it in descending order. Okay, sorted. Now I have to remove the first element and according to the weight mark the remaining element. So I have marked this. Then what? Then from the marked element I have to remove 1. So this is 1 minus 1 and this is 0 So this is 1 minus 1 is 0. So what I'm getting is 0. So once I get 0, then it is now confirmed that the graph is an example of a simple graph. The graph is possible, that means it is graphical and it is simple graph. So in this way, friends, we proceed to evaluate that whether a given degree sequence for a graph represents a simple graph or not. Let us take one more example to understand this theorem more. So let us consider the degree sequence as 5, 5, 4, 3, 3, 2, 2, 2, 1, 1. Now, what has to be checked first? The first thing first which we have to check is the degree sequence. So if I add 5 plus 5 plus 4 plus 3 plus 3 plus 2 plus 2 plus 2 plus 1 plus 1. So 5 plus 5, 10. This is 3, 3, 6 plus 4, 10. 2, 4, 6 and this is 8. So the total is will come as 28. So that is an even number. Very good. Then we have to check whether any number is negative or not. So there are no negative degrees in the sequence. So now we are ready to move to Hevel-Hakimi theorem. So the iteration one says we have to write everything in descending order. So already the sequence is in descending order. So we needn't have to worry about that. Now we have to remove the first element and mark the elements after it based on the weight. So it is 5. So 1, 2, 3, 4, 5. So 5 elements I have marked. Then what? Then I have to remove 1 from all the marked elements. So it becomes 4. This becomes 3. This becomes 2. This becomes 2. And this becomes 1. And then the remaining elements. That is 2, 2, 1, 1. Okay, now comes the next iteration. So in iteration 2, what I have to do? I have to sort this. So 4 is already there. Then this 3, okay, this will come as such. These two 2's will come and then there are two 2's more. And then 1 and then 1 and then 1. Then I have to do what? I have to mark this element. That means I have to remove this element and mark the elements according to the weight of this element. So 1, 2, 3, 4 elements I have marked. Okay, and then I have to remove 1 from these marked elements. So this will become 2, this will become 1, this will become 1, this will become 1, and then 2, 1, 1, 1 will come as such. Okay, now we are heading to the third iteration. So what we have done is we have done till this point. Now we have to arrange this in descending order. So 2, 2, 1, 1, 1, 1, 1, 1, and then 1, 1, 1. So 1, 1, 1. Now I have to remove this, and according to the weight I have to mark the elements. So 2 elements have to be marked. Then this is 2 minus 1, that is 1, 1 minus 1, that is 0, and then remaining ones 1, 1, 1, 1, and 1. Then what? Then in the fourth iteration, I have to arrange all the numbers in descending order. Let me check the ones 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Okay, then I have to remove this and mark the element according to its weight. So it is coming as only one element. So we have to remove 1 from this. So it will become 0, 1, 1, 1, 1, 0. Then write in descending order. So it is 1, 1, 1, 1, 0, 0. Then do what? Then remove this, mark this, and then so this is basically your iteration number 5. Then this 1 minus 1 will become 0, and next two ones will come as such. Then it comes your sixth iteration. In the sixth iteration you have to do what? You have to sort this in descending order. So it is 1, 1, 0, 0, 0. So you have to remove this and mark, and then you will be getting 0, 0, 0, 0. So everywhere you are getting what? 0, and hence the original sequence is graphical. That is, it represents what? It represents a possible case of simple graph. So remember that this particular theorem, that is Havel-Hakimi theorem, is for checking that whether a given degree sequence is graphical or not for simple graph. And first we have to arrange the elements in descending order. Then we have to remove the first element and mark the elements according to the weight of removed element. Then from the marked element remove one and then proceed this, continue doing this. Now if in between it so happened that the removed element weight is more than the elements which are in the sequence, then that is not graphical. And once after doing this continuously, it came that all the elements are becoming 0, so that is graphical. And if they are coming either negative or we cannot subtract any further, we are getting something which is non-zero, then again also it will be non-graphical. So in this lecture, till this point only, in the next lecture we will be learning about few more concepts. Thank you very much for watching the video.